We physicists have anticipated this photograph for a century. Since 1916, this image pertains to black holes, which might be among the most captivating and enigmatic phenomena in the universe. They are colossal entities in terms of power but are nearly invisible to us. A black hole with a mass potentially 2 to 4 million times that of the Sun has been studied extensively over recent decades. This research has shifted our understanding from knowing nothing about them to exploring their details up close. Recently, Michio Kaku announced that we have finally glimpsed the inside of a black hole, and this new information sheds light on details previously overlooked by the scientific community. Join us as we delve deeper into black holes and reveal what lies within. Space is vast, so what are black holes? Before delving into Maka's findings, it's essential to discuss the basics. Despite some general awareness, there are still gaps in our knowledge about black holes. In 1916, Albert Einstein published his theory of general relativity, which predicted the existence of black holes. At that time, black holes were purely theoretical. It took another 50 years for the scientific community to find evidence confirming their existence. This breakthrough occurred in the 1960s when astronomers studying the Cygnus X1 constellation observed an unusually bright blue star emitting X-rays. This star was not stationary but orbiting around a massive black object. Further investigation revealed that the X-rays were being drawn into this black object, leading to its designation as a black hole. This discovery was crucial, as it validated that black holes were not just a product of Einstein's imagination but real entities in space. The discovery led researchers worldwide to investigate further, uncovering that Cygnus X1, located about 6,000 light-years from Earth in the Cygnus constellation, is approximately 14 times brighter than the Sun and extremely dense, exerting a gravitational pull so strong that not even light can escape it. This intense gravity is why it is termed a black hole. The concept of a black hole is both intriguing and alarming. It represents a region of space where gravity is so intense that nothing, not even light, can escape. Anything that ventures too close to a black hole is pulled in, never to be seen again. This aspect of danger makes understanding black holes even more critical. Following the discovery of Cygnus X1, scientists sought other black holes and estimated that there could be over 100 million in the Milky Way alone. However, due to their elusive nature, the exact number remains unknown. Despite this, it appears there are several million black holes in our galaxy, underscoring their importance in scientific research. Let's break it down. The primary concern with black holes is their gravity. Their gravitational force is so extreme that anything entering them presses down to a singularity. Essentially, black holes act like cosmic vacuum cleaners, drawing everything into them. One of the most unsettling aspects of black hole research is that if someone were to fall into one, they would be stretched into a thin line, a process occurring gradually until the person perishes before the final state is reached. Therefore, it is wise to avoid black holes. Though their presence is widespread, the closest black hole to Earth is approximately 1,500 light-years away, a distance that raises questions and concerns. In 2021, scientists captured the first clear photograph of a black hole, specifically the M87 black hole. This black hole was photographed over several nights, with each image providing additional evidence. By stitching these photos together, researchers determined that black holes have 3 distinct layers. Contrary to the belief that black holes are merely vast voids, they are far more complex. To reach the void within a black hole, one must first traverse the initial 2 layers. The first layer, known as the event horizon, marks the point of no return. Once crossed, there is no turning back, and one is inexorably pulled into the black hole. The second layer is the photon sphere, where light orbits the black hole. Light entering this region is trapped and cannot escape the gravitational pull. The third layer is the singularity, where everything that enters is compressed to an infinitely small point. At this stage, the laws of physics as we understand them break down, making predictions impossible. What complicates matters further is that each black hole studied is unique. While they generally follow the 3-layer model, their functionality can vary greatly. Unlike other objects that can be studied directly, black holes can only be examined indirectly through the radiation they emit and the surrounding gas and dust. Sending a probe, like Voyager, into a black hole is not feasible because anything entering the event horizon is pulled towards the singularity and compressed to an infinitesimally small point. Therefore, billions of dollars cannot be spent on probes that would be destroyed instantly. This limitation forces scientists to study black holes in a two-dimensional manner, even though they are three-dimensional phenomena. Moreover, every black hole is unique, and the breakdown of physics when exploring their interiors adds to the complexity. Traditional scientific methods are inadequate for studying black holes, leading to numerous theories and explanations. One compelling theory suggests that black holes form from collapsing stars. When a star exhausts its fuel, it can no longer counteract gravity's inward pull, causing it to collapse into a singularity. If massive enough, NASA scientists focused on the core of the galaxy M87 to understand black holes better. They observed a powerful whirlpool of superheated hydrogen gas spinning at an astounding rate of 1.2 million miles per hour. The spinning disk should have flown apart, but it didn't. Scientists inferred that a massive object weighing 2 to 3 billion suns must exist at the center of the galaxy to prevent this. This object could only be a black hole. Another theory, proposed by New Zealand mathematician Roy Kerr in 1963, describes spinning black holes. Kerr showed that a spinning black hole does not collapse into a point but into a ring of fire or thin disk. The disk spins so rapidly that centrifugal forces prevent collapse, forming the ergosphere, a region around the black hole where physics begins to break down. Kerr's solution also predicted the existence of an Einstein-Rosen bridge or wormhole, a theoretical passage through spacetime connecting two separate regions or even parallel universes. According to this theory, falling into a black hole might not lead to destruction but instead through a tunnel to a white hole in another universe. To understand this, consider Einstein's theory of spacetime, where space and time are interconnected, forming a four-dimensional fabric. Objects with mass warp this fabric, creating gravitational fields. Imagine a sheet of paper representing spacetime. If you place 2 points on it and draw a line between them, it shows how objects move through spacetime. If you fold the paper to create a shortcut between the points, it represents a wormhole, a shortcut through spacetime connecting distant points instantly. Wormholes are not just science fiction. They are predicted by general relativity, though no one has observed one directly due to their instability. However, an Einstein-Rosen bridge would suggest that black holes might be pathways to other regions of spacetime. The feasibility of using a wormhole for space or time travel is questionable, as even if we could stabilize one, traveling faster than light is unlikely due to Einstein's theory of special relativity. The concept of wormholes as pathways to distant parts of the universe or different times is fascinating and speculative. The CER wormhole, named after Roy Kerr, is a hypothetical tube through spacetime connecting two distant points. It is ring-shaped and might allow travel to other universes or times with different physical laws. However, the idea of wormholes as a means of travel is controversial. Critics argue that wormholes, particularly Kerr wormholes, might be unstable or impossible to traverse due to intense radiation and subatomic forces at their entrances. Einstein's equations of gravity describe wormholes and black holes but do not account for quantum forces, necessitating a unified theory combining gravity and quantum theory, a theory of everything. Michio Kaku, a renowned theoretical physicist, has worked on such a theory for decades. Among the various proposals, superstring theory has shown promise. It suggests that subatomic particles are tiny vibrating strings and that the universe is a symphony of these strings. Just as musical notes correspond to different vibrations on a violin string, particles correspond to vibrations of superstrings. Superstring theory not only unites gravity with quantum theory but also explains many cosmic phenomena. However, the extra dimensions required by superstring theory are so tiny that they are currently undetectable. The most accurate measurements we can make are within the 4 familiar dimensions of space and time. One possibility is that these extra dimensions are curled up tightly, making them invisible to us, much like a tightly rolled up sheet of paper. Another possibility is that these dimensions were more visible at the universe's birth during the Big Bang. According to some versions of superstring theory, the universe began in a state of 10-dimensional spacetime with all dimensions visible. As the universe expanded and cooled, extra dimensions collapsed and curled up, leaving the 4 dimensions we observe today. If correct, traces of these extra dimensions might be detectable. The mathematics of superstring theory is highly complex and has opened new areas of mathematics. However, solving the problem of a quantum black hole remains elusive. Edward Witten of the Institute for Advanced Study at Princeton has described superstring theory as 21st century physics accidentally arriving in the 20th century. Recently, physicists have announced a breakthrough, finding that string theory could solve the quantum black hole problem but only in 2 dimensions, not 10. Many physicists believe it's only a matter of time before this problem is solved, given that the equations are well-defined but challenging. Until then, intergalactic travel and time travel remain speculative. Despite the progress, there are still many questions and potential solutions. Michio Kaku's string theory suggests a different perspective on black holes and spacetime, possibly reshaping our understanding of the universe.